session of CISR seminar for this new semester, new academic year, on this beautiful 1st of October day. Those of you who are new to CISR, especially welcome. You will be getting an email next week, I hope, where you will get an orientation meeting, but there is no greater way to start your CISR involvement than with a seminar. Those of you who are in CISR and you are returning students who have participated in the program last year, welcome back. And everybody else who is joining today for this session, welcome. I'd like to say welcome. I have the great pleasure today to introduce the speaker, Dr. Thomas Gilray. Tom is a new professor who joined us here at WSU just this semester. He was an assistant professor at the University of Alabama in Brigham, and before then he was with the University of Maryland as a Victor Basil Fellow. His area is in programming language primarily and works in a number of different things, including high-performance computing. We've had some long chats. Anybody who says I have interest in graph algorithms and high-performance computing gets my ears, and he did have that ears for a long time. So I'm very excited today for what he would be talking about. He does work in things that have got relevance to security and privacy, which is the subject for his talk today. Correctness and verification using software. Using software contracts is the title of his seminar. We have 50 minutes. He would leave, I hope, some 5-10 minutes towards the end for questions. I would like you to do is, as the presentation goes on, if you have questions, you can put them in the chat and we will address them at the very end. If there are quick things that he can clarify along the way, he may do that. I also want to remind you, CISR students, at the very end, we're towards getting close to it, James would share a link for a quick survey so that we know you were here and get your feedback. So take the time to do that. If you have a class to run to right after the talk is done, maybe you can do this after your next class, but otherwise take the 10 minutes or so that's needed to complete that survey because it's a helpful feedback. So I don't want to run too much into this time. I'm very much looking forward to this presentation, Tom. So take it away and welcome.
Thanks. Thank you. Thanks for the nice introduction, Asifa. I'm also very glad to have the opportunity to chat with you all today. I'm going to be talking a bit about software correctness and verification, basically from a programming languages perspective and kind of formal methods perspective, and looking to introduce you all to the idea of software contracts. This will give me a bit of an opportunity as well to say something about my own research vision and some of the techniques that I've been working on. So I mostly work on program analysis, reasoning about code, being able to audit code and model code, also developing new languages and high performance parallel systems for reasoning tasks generally, kind of grounded in this application of program analysis that has driven a lot of my work. So as I said, my own research background is mostly in programming languages, formal methods, and some kind of related areas like that, high performance computing. But I think my interests have a lot of relevance to cybersecurity, how we might audit and secure code. So I hope it'll be of interest to all of you. I'm sure I don't have to tell you that as software continues to become more powerful and useful, it kind of pervades all aspects of our lives. So critical software is in cyber infrastructure. It's used for medical robotics, airplanes, and cars. I think an interesting thing I learned a few years back was that cars increasingly have quite a number of processors in them now. And so lower end cars will have at least a few dozen processors, and higher end cars have consistently more than 100 different processors in them. And so it's incredibly important that we care about software correctness, security, and privacy properties, given how ubiquitous software has become and how many kind of critical applications that it's found its way into. You may recall a number of years back there was an issue with Toyota vehicles having unintended acceleration issues. And I thought it was interesting that in one of the court cases on this, they had an external auditor look at the code, and basically he reported that Toyota's code for their vehicles was riddled with bugs and spaghetti-like. And I think that's probably not surprising to a lot of us that this would be the case. And why is this? I think one of the things that I would pin this on is this kind of idea of what we might call worse is better. And what is worse is better? It kind of refers to this idea that that often our priorities are misaligned. And for example, we might care more about getting code to market faster or producing something that's kind of good enough and has the appearances of working code, but it doesn't necessarily have to actually be better code. And so in some cases, paradoxically, code that is worse is really better in terms of the incentive structures that are around that code and that are building that code, basically. And one thing that I would, a perspective that I like to take on this, I guess, is that often when developing software, there's more sort of firm or discrete concerns, and then softer, more continuous concerns, right? And they both matter, but often discrete concerns are more all or nothing, right? So these are things like correctness properties, security properties. Can the program go wrong in some particular way? Will it exhibit a certain class of bugs? Is it exploitable or vulnerable in some way? And so it's sort of all or nothing. As you all know, coming from a security perspective, if code can be exploited, it can be exploited, right? And it doesn't matter if it's a bit difficult to exploit it or if there's only one narrow avenue for exploitation. If there's a way around the wall, people are going to go around the wall and not through the wall, right? But there's often also more kind of soft, continuous concerns that also matter to people. So this might be things like the simplicity of the code, the maintainability of the code, the elegance of the code, the time to market, how quickly can the code be released, performance and optimization. Can we squeeze a few percent? Can we squeeze just a little bit more performance out of the code and get the timings down just a little bit? Are there some optional features that maybe aren't completely critical, but that would be nice to have? And can we extend some of the features and niceties of the code? And I think worse is better often comes from some kind of mix-up that occurs between these different concerns, right? We sometimes confuse more continuous concerns for discrete concerns or vice versa, and sometimes prioritize things like time to market or performance over, or some of the nice to have features, say, over the fundamental correctness of the software and making sure that it meets some correctness specification or some security specification that we care about. So what's an example of this? I think we've all probably used this idea of test-driven development. Certainly I write all of my own code this way, right? You sort of first start thinking about some simple test cases and you write those up, and then you start writing your code and you check the test cases on your code and you make sure they work, and then you write some more test cases and you try to make sure that you're confident your code is working from a testing perspective. And this gives you a great sanity check, right, on the code that you're writing, and gives you a good sense of confidence that what you've written is correct. If the code looks correct, the code ideally in some sense represents its own specification, right? The code is a specification you're giving to the computer to say, what you want it to do. And ideally you'd want self-documenting code, right? And then if you have a number of tests that are also giving you some extra assurance that in a black box way that it's extensionally doing what you'd like it to be doing, then that gives you a sense that you've written correct code. But ultimately, even if we were to write more and more and more tests, the tests are an under approximation of the real behavior that we want out of our code, right? And so there's some set of true program requirements that goes around these tests. And in some sense, there's no number of tests that we could enumerate that would ever really flesh out the full scope of the true program requirements that we have. And so although this is very tempting, what we really might want is something more like a specification-driven development, right? Where we design a specification carefully on paper, and we pin down all the critical program properties that we care about, and then we go and we write our code based on that. And we don't do that because of this sort of worse is better notion that really it's much faster to just start writing some test cases and to build up things ad hoc. In fact, the flow diagram that I'm showing here on the left is written by Donald Knuth for a compiler that he wrote in 1959, and I thought that was kind of interesting. And you know, in the early days of computer science, there really were a number of pioneers, you know, Knuth, Dijkstra, and others who were sort of saying, you really want to write down all of the program properties that you care about before you write your code, rigorously mathematically prove them, and then and only then can you write your code with an assurance that it's going to be correct, right? But of course, you know, we don't do that because really it's through the success of software that we don't do that. It's so easy and fast to rapidly prototype things with such nice high-level languages and all the great tooling that we have nowadays. You know, you might even be able to go put, you know, an English description of what you want into ChatGPT or something now and extract some good boilerplate code that you could start with, and then you write a few tests, and within 10 minutes you've got something that's almost correct. And so it's very tempting to do that instead of starting with a blueprint of what you're looking to design. And really pinning down all the properties that you care about. So what I would advocate, and what I want to talk to you about today, is sort of a middle of the road approach that tries to sort of bridge this gap and fuse these two perspectives and help us to write a specification in a more incremental way, right? And this is sort of the idea of contract-driven development, or what we could call design by contract, and has famously been called design by contract. And this is more the idea of writing your code in a self-documenting way that includes pieces of your specification right there in the code, right? So you're writing your code, and alongside your code, you're adding in these contracts, which basically guard your code and impose specification on it and requirements on it that help to ensure that your code is correct. So this helps to make it more self-documenting, and also is something that actually runs along with your code to monitor your code and enforce correctness. So what is a contract? Well, a contract is basically an agreement between multiple parties for mutual benefit, and we want the agreement to be enforced, and we want violations to be blamed on the offending party. So let me give you an example of this. Let's say we're writing a reallocating array class in C++. And so we've got an insert method here, and it takes a reference to an element that we're trying to insert, and it takes an index at which we're inserting it. And at the top, I've added an assertion which says that the length of the array has to be at least as long as the index we're trying to insert it at. So we could be inserting at index 0, or we could be inserting at index length, or anywhere in between. But you know, we don't want to be inserting off the end of our array, right? And so we could add this as an assertion statement, right? And this represents a kind of precondition for running the code. It represents a requirement of the caller for this code that you can't provide me an index that goes off the end, because if I start running this code with an index that goes off the end of my array, then bad things could happen. So if we sort of snip out the middle part of this code, which represents actually doing the work of inserting that element and maybe some possible reallocation of the underlying buffer for the array, we could see at the end of this code, we might also want a post condition, and we could use an assertion for that as well. So this would say, well, maybe if we reallocate, we insert a new element, we had only exactly the amount of space we need. A reallocating array class might reallocate the underlying buffer with twice the length, say, and then copy all of the elements in. And now you have the ability to do efficient insertions in an amortized way, at least. And so if we're doing this, at the end, we might want to make sure that we've maintained an invariant that says the length is no longer than our buffer length. We might add to our precondition to say that at the beginning also, this should be an invariant that at both the beginning and end of our insertion, our length is no longer than the buffer that stores it. So these are, in a sense, pieces of code that we've added to our code that helps us to enforce properties that we care about, right? And this is basically the idea of design by contract. So this emerged in the Eiffel programming language, which is a typed object-oriented programming language with contracts sort of at the center. And one of the famous phrases that Bertrand Meyer used to describe the approach that he was taking with Eiffel is that he wanted to encourage design by contract. So, in talking to people who are enthusiastic about type-based typed programming languages, strongly typed programming languages, say you often hear people say, isn't it always the case that when you first think of a piece of code, you always think of the types first? You think of the type specification, and then you start to flesh it out with all the details of how the algorithm would actually work. You first think at an abstract course level about this component of your software, and then you think about the details, and you get more and more detailed until you have the whole thing worked out. And each of these layers of abstraction sort of has to respect the others. And that's also the idea of this design by contract, right? It's sort of the idea that you would start with an abstract specification for your code, and you would write this up as a contract, and then you would think about the details of how do you write code that then respects that contract. And another phrase that he used is that a contract carries mutual obligations and benefits. And that's kind of the idea. And it goes with this idea of having preconditions and postconditions. So here's a piece of Eiffel code kind of showing this in its original language. So this is adding a child to a tree, put child, it takes a node, and it requires basically that if node is nullable, that it's not void. You're not passing in something null. So if you're more familiar with Java, then think about passing in a reference that could be null, and you want to make sure that you're not actually passing in a null reference. So you could check that. And there's a require block at the top that basically lists out some statements that say what are the preconditions for this component of your code. And so in this case, it says, well, the new node that I'm inserting can't be null. And then at the end, there's an ensure block that basically says, here's what I'm ensuring after the code is done running. And so these represent basically preconditions and postconditions that you're able to insert directly into your code. And so how does this work? Well, when you call put child, then there's basically a contract and code for the contract that is interposed between the call and the code being run. And so it's going to check this precondition, and the code that's calling put child has to satisfy this precondition as an obligation. And then if it satisfies the obligation, the code can run, and the post condition will be checked. And so the component will also provide a benefit, which is that it'll guarantee the post conditions are going to be met as well. And if the client breaks the code, then put child is not obligated to provide its benefits. And in fact, the code shouldn't run. So if we pass in null, then there's a requirement. The contract is guarding the code and basically saying, well, you're not actually allowed to run this code if you didn't satisfy the requirements. So contracts are really a linguistic mechanism that can be implemented as a built-in feature of the language, or can just be a source-to-source translation, some external tool that takes in source code and then translates it into source code that basically embeds these assertions into the code. Or it could be a macro system. So the language could support basically expanding these contract declarations, which can be stated at this nice high-level declarative way, sort of like type declarations, and can expand them into code that checks the contract and dynamically monitors for these properties as the code is running. So this has been built into lots of different programming languages. So probably most of the languages that you like using and you're familiar with would support some kind of a contract system at this point. So for Java, for example, there's a system called JContract. And in JContract's case, it's really a source-to-source translation that takes comments that you can put in your code and then embeds them as assertions into the code. So for example, you can put comments above your function that say what the precondition is and what the post condition is, like in this factorial example. So the precondition might say my input has to be greater than or equal to 0, and as long as the input is greater than or equal to 0, then the return value is going to be greater than or equal to 1. And so in the J contract language, you can use return as a keyword to basically say, to reference the value, the return value. And then what J contract will do is basically expand this into a piece of code that has these assertions. So it's going to put an assertion at the top that checks for the precondition. And then if there are multiple different return points, as in this example, it's going to put an assertion before each of those return points to check the post condition. So a key thing to note is that this is really a dynamic monitor. It's actually running this code every single time you run factorial. So in a way, it's turning every run of your program into a test case, right? Instead of breaking in some nastier way, which perhaps could lead to an exploit, it's going to break in a safer way and tell you, no, this isn't obeying my contract. And a language that I really like to use a lot in my work is Racket, which is a dialective scheme. And Racket has also been very pioneering in contract systems and macro systems. It's sometimes been described as a language-oriented programming language. And the idea there basically is that it has a very powerful procedural macro system that allows you to write code in Racket to expand on the features of Racket. So you can write your own language forms by just writing a library of Racket code. And so you can write a library which basically extends the language. So you can sort of write an extension to the language just as a normal library. And so this has been done for a contract system. And because it's a functional programming language, it's also been an opportunity for interesting work in terms of expanding the expressive power of contract systems to functional languages and looking at how to do that in a proper way. Another good example of this is sort of building on the same idea is contracts.js. So contracts.js is a library built with hygienic macros for JavaScript. So it's sort of this language-oriented programming approach where the author wrote a contract system as a library that then extends JavaScript using macros. And you can actually play around with this yourself. So you can go online right now if you want and put this URL in, and it basically gives you a little sandbox where you can play around with some examples of contracts in JavaScript. So I'll show you an example of this as a way of fleshing out some of what I've been talking about more. Let's say we have an array number to string function. It takes in an array, and it's gonna convert all the numbers in this array to strings. So that's what this code does. And we could add assertions at the top that check, for example, that we have an array at the beginning, an array at the end. And basically, this corresponds to a comment-based specification that says, well, we have an array of numbers and we're turning it into an array of strings. And if we wanted to check that each of the elements was a number and each of the elements was a string, we could expand our assertion. And this all gets rather complicated. So basically what the contract system as a macro is able to do for us is allow us to write this up in a nice way using an at macro. So we can write it up like this and say, this array num2stir is a function that takes in an array of numbers and then gives back an array of strings. And now the contract system will instrument this code for us to add in those assertions that dynamically monitor for this property. But what if we want to be able to format the string in a special way? So let's say instead we want to get back something like a hexadecimal representation, like I show here at the bottom. Well, then maybe we could expand this to add to make it a higher order function that takes a format function as a parameter, which is a num2stir function, which takes each of the numbers in our array and turns it into a string. So now we can parameterize this code by our own formatting code to have it format these strings however we want. And so if we do that, then we get this code back out. But how do we check for this, right? So I showed you an example of adding assertions at the top, and we're able to just, the moment we jump into this function, check that the precondition is being satisfied. But one of the preconditions is really here that a first-class function that we're passing into this function to parameterize it has a specification that says it takes numbers to strings. And we can't actually introspect on that function to check that in a greedy fashion or an eager fashion, right off the bat when we run this code. And so the idea is that basically we have to delay evaluation of this contract for the format function until the format function is run, right? So we're just sort of treating this recursively. When we write a specification for array num to stir, it's not checked when we first run the code. It's only checked when array num to stir is actually run. And so the same thing is true of the format function. So the principle here is that contracts on behavioral values are delayed. And this comes from Findler and Felisen style contracts written in Racket originally, and is now used ubiquitously in different contract systems for higher order languages. So let's say we instead just pass it the identity function. So it's going to take in a number and it's not going to do anything with it, and it's just going to give us back a number. Well, then it's going to hit an error on this line, right? Because when we run the format function, it's then going to have its own contract that says I have to be a num to stir function, and that's going to break. But really, the bug was down here at the call to array num to stir, where I have an arrow here. So this is the idea of being able to assign blame correctly when a contract is violated. So if you run this in contract.js, you'll get a contract violation, and it'll tell you that the context, the calling context for array num to stir is actually to blame because it passed in a format function which wasn't valid. So part of what has to happen is that in a higher order contract system, we have to be able to track program labels along with these contracts so that we can assign blame properly. And there's been a series of papers by Christos Dimilas on this topic and how to handle all of these things properly when interacting with a number of the different features that are in Racket. And one thing that's important to note about this is that really our contracts can be written with arbitrary code in our host language, right? So in the language that we're using to write our application logic, we can also write arbitrary contract code. So for example, if we wanted to check the length of the string, the length of the array that we pass in is the same as the length of the array that we're getting back out, we can do this and add a condition, post condition that checks for that. And really, we could write our own function alongside our application logic that is then called by this contract declaration to do an arbitrary amount of work. So there's really a lot of expressive power here because we can write arbitrary code to monitor our own code. And you might be thinking this is very similar to what type systems are doing, especially with some of the examples that I've given. And actually, there are type systems that are more expressive than typical type systems that cannot guarantee efficient type checking, in fact, in general, because they're so expressive, which allow you to embed logical statements in your types that refine those types. And so these are called refinement types. But if we compare the principles of software contracts to static type checking, we see that they have sort of some different properties, right? So with software contracts, we have the exact same expressivity as the host language. Anything we can write in the host language, we can put into a contract. With static type checking, we have to have a separate type language, which we could make very sophisticated, but it has to be defined separately. With software contracts, we report actual and observed errors, and we give witnesses to errors. With static type checking, we report potential errors in abstract terms. So they don't necessarily even correspond to real errors in every case. With software contracts, it adds significant runtime overhead. It breaks tail calls and things like that. And with static type checking, we can produce fast code that doesn't have runtime monitoring. With software contracts, our error discovery is delayed because we are treating each run of the code as a test case, basically. And with static type checking, our potential failures are discovered ahead of time. So I'd say one of my research, part of the vision of my own research is to use software contracts to help bridge this gap between the advantages of a static type checking system and the advantages of a dynamic contract system. And I think the future of dynamically enforced contracts is static verification. And the really nice thing about contracts is that we can do this in a piecemeal way, sort of one step at a time. So I sort of envision a bridge from dynamic enforcement of program properties using software contracts to formal verification of program properties, um, where we're able to verify one contract at a time. And in cases where we can't verify a contract, then we could just leave the contract residual in the code as a dynamic monitor. So we still get the benefits of the software contract, even if we couldn't turn it into ahead of time verification. And so to give you kind of a high level sense of some of how this works, in a functional programming language, if we have a piece of code here that an F that takes a first class function G, if we want to know where control can flow at this call G of Y, then that depends on the data flow to G, which in turn depends on the callers to F. So if we have a few different callers to F like this, then we end up with some different possible values for G, which then gives us possible places that control can flow from F when we call G. And so this is called the higher order control flow problem. And it's really the entanglement of control flow and data flow. And to tackle this problem, we use AI, although not this kind of AI, abstract interpretation in this case. And abstract interpretation is basically a way of reasoning about code in the abstract, using approximations of the code and abstractions for the code, instead of reasoning about the code in precise terms by evaluating the code. And this is something that we do all the time in day-to-day life, right? I mean, I might say to somebody, do you know the way? And they say, well, sure, you just take a left at the tree, past the tree there. And I say, the little poplar just there, and they might respond, oh no, the tree with 51 branches and 8,200 leaves. Of course they wouldn't, because this is sort of striking the wrong degree of precision, right? It's way too much precision. We don't need that much precision. It'd be much better just to say, ah no, the large oak tree over there. So as human beings, we're very adept at being able to negotiate the right level of abstraction that we should be reasoning about things in terms of. And part of the idea here in reasoning about code is that we want to be able to do the same for code. We want to be able to reason about code at the right level of abstraction. So we construe a kind of lattice of different abstractions that we could use, where at the very top it just says, well, it's a thing, and a little bit lower in the lattice we have tree, and a little bit lower we might have large oak tree, and then way down here at the bottom we've got very specific properties, like it has 51 branches and 8,200 leaves. And because it's a lattice, we also have meets and joins. So we can take basically the conjunction of different properties or the disjunction of different properties. And what we can do then is basically use abstract interpretation to develop from a concrete interpreter a system that reasons about our code. So a concrete interpreter is going to take a program and inject it into some initial state or some representation of the state, and then just iterate a function that tells us how do we step through the program and interpret the program step by step. This is at least how an operational interpreter would work. And this gives us an execution trace for our program. And if we sort of zoom in on one of these states, the state is going to be modeling various aspects of our program with enough precision to be able to evaluate the program precisely. So it's going to tell us the program counter maybe, or the line of code that we're on, the binding environment. It's going to have a model of the heap, maybe a model of the stack. And all of these are going to have to be quite precise so that we know exactly how to run our code. And if we run a piece of code like this, let's say this is a piece of Java code that computes the next odd number. And so it's got a post condition that says it's not an even number. I guess that's how we're defining it, as an odd number. And if we pass in 9, we get back 11. If we pass in all possible integers, then we get back all possible odd numbers. And basically what abstract interpretation does is gives us a tool set to be able to reason about this in the abstract to prove, even though we couldn't pass in all possible numbers and see that we're getting back only odd, or sorry, we can't pass in all possible numbers and see we're only getting back odd numbers. We can reason about our code in a way that allows us to determine that in a closed form way. And so in doing this, we need to be able to take joins of different possible values that are coming in, and then recognize that we basically want to model this lattice in terms of just abstractions like even and odd. So even and odd in this case are the right level of precision for reasoning about this problem. And abstract interpretation is basically based around an idea called the Galois connection, where we have a pair of functions that define abstraction and concretization on these lattices, which is basically a weakening of lattice isomorphism that lets us basically connect two lattices that represent the same thing at different levels of granularity. So we can basically pull out unnecessary degrees of granularity and then reason about our code just in terms of the degrees of granularity that we care about, which is much more efficient, but if we design our abstractions right, is able to give us the benefit of verifying properties about the code that we care about. So that's the idea. And abstract interpretation advocates for what's called the calculational approach, where you can take a concrete interpreter and an abstract specification, a specification of abstractions, which you can then put together to come up with the exact proper abstract interpreter that you would want for this. And so the idea here basically is just intuitively, we know if we add together two odd numbers, we always get back an even number. If we add together two even numbers, we always get back an even number. But if we add together an even and an odd number, we get back an odd number. And so that's really what abstract interpretation is allowing us to do for this example in a rigorous way. So we can sort of reason in a closed form way that we can produce an abstract plus that lets us interpret plus in terms of these abstractions instead of in terms of concrete numbers. And so in the end, what this allows us to do basically is come up with an abstract state that represents our initial state, and then iterate an abstract transfer function on that state, which builds up a non-deterministic but closed abstract model of our program. And the key property here is basically that this closed abstract model of the program includes all possible, or an abstraction for all possible concrete program traces. So if we were to line up our execution trace against this, we would see that it's represented by some path through this abstract model. And so this represents basically a soundness condition, that all observable behaviors must be represented in our model. And so usually we're going to want to design our abstract interpretation so that we have false positives, but not false negatives, for example, or vice versa. So if it's an over approximation, we'd have false positives, but we don't have false negatives. And what that means is if our model excludes a behavior and the way that we develop this model is sound, then that tells us that actually that behavior can be proven not to be exhibited by this code under all possible execution traces. And so that's really how we can get from just having a set of tests that give us a sanity check that our code is correct, and get to an actual verification that our code is indeed fully correct. And so the last thing I want to talk to you about is how we can really take this technique and make it heavyweight enough to verify contracts, right? Because what this basically does so far is it allows us to build an abstract model of our code. And it's great at doing sort of finite flow analysis types of things. Where can which kinds of values flow and propagate in the program? But when we really want to build a reason about values, we have to come up with these abstractions for our values, like I was showing you with even and odd. And that can be difficult to do for all possible types of values that we want to support, especially when users are writing code to build up complex data structures of their own. And so what we'd like to be able to do, and what collaborators and I have proposed, is combining abstract interpretation with something called symbolic execution to really turn symbolic execution into a method for full verification. So symbolic execution is really a way of auditing code and finding bugs and helping to assist in in checking that code is correct, but it doesn't really naturally give us a way to do full verification. The idea of symbolic execution, to go back to this original example of an insertion method for a reallocating array, is that as we step over this code, we consider all possible ways of moving through this code. So whenever we hit a branch or a jump, we take all possible branches, and then we just consider what must be true down these different branches. So if we expand these preconditions and postconditions, which we've been representing as assertions so far, we can see really those are also macros that are just expanding into guards that are saying, well, if the assertion is not true, well then hit an error, right? And so assert is also just a macro that expands into an if. And when we pass through this if, we can just consider both possible branches. Either we did hit the error or we didn't hit the error. And what symbolic execution basically has us do is associate with each possible value what's called a symbol that sort of represents the value. And then we can build up what's called a path condition, which is a formula that has added to it. It's basically a big conjunction of all the different properties in terms of these symbols that had to be true. So for example, if we hit this error, then we might want to be able to see that we basically would be adding to our path condition something that says alpha, which represents this, dot length is less than gamma. And so down one branch, we're going to say alpha dot length is less than gamma, and down the other branch, we're going to say alpha dot length is greater than or equal to gamma. And we just explore paths going outwards, trying all possibilities. And then it's possible that we can find contradictions, places where two things that we added to our path condition can't both be true, right? Alpha dot length can't both be less than gamma and greater than gamma. And when that's the case, then we know that that's not a feasible path. And so symbolic execution gives us a way of doing this to hone in on the places where there might be errors. But if we go back to our idea of producing a closed abstract model of our program, if we've done that, then our path conditions naturally become over-approximate. They become weaker path conditions, really. But these path conditions, when they can be verified, really give us a strong claim that we can make about our code, which is that a state cannot possibly be reached. So if we look at one of these abstract states with an abstract over-approximate path condition, then we can take that formula and we can throw it into a black box XMT solver like Z3 or CBC5, and it'll tell us whether it's satisfiable or not. And when we have an unsatisfiable formula that is an over-approximation of the behavior at that of the path condition at that state, then we can prove that that state is not reachable. And so we might have various unreachable program states that we can remove from our model on this basis. And if one of those program states represented an unreachable contract failure, then we've actually genuinely verified that contract. And so where we've verified a contract, we can then remove this dynamic instrumentation we've added to our code that dynamically monitors that for that property. So in summary, contracts are a linguistic mechanism for embedding dynamic monitors to enforce program correctness. And this gives us a precise runtime bound that defines concrete behavior. So it sort of turns each of our runs of the program into a test case. Unfortunately, this adds significant runtime overhead and delays error discovery until runtime. But with some of the techniques that collaborators and I have been working on, including abstract symbolic execution, I think we have ways of being able to verify contracts on a best effort basis to identify where contracts cannot fail and remove those contracts from the code. And so in the paper that I cited on a slide or two ago, for example, we performed this on a suite of racket benchmarks, and this suite of benchmarks had in total roughly 50,000, just under 50,000 different dynamic checks from contracts that were being inserted in the code. And in practice, in our experiments, we were able to verify all but about 30 of them, I think 29 of them. And of those 29, a few of them were actually genuine errors that we discovered in the benchmark suite, and then the rest were basically cases where we couldn't model the program with enough precision by picking abstractions ahead of time that suited our analysis of the program to be able to determine that they were something that we could verify. But the nice thing is that in those cases, we have this piecemeal approach to verification that allows us to leave those dynamic monitors in the code so that at least we have the benefits of contract monitoring in the cases where we can't perform full verification. So thank you for your time, and I'll be happy to use the time we have left to answer any questions you might have.
Wonderful. Thank you very much, Tom. That was really fascinating talk. I'm sure there are students who have not had a chance to take courses in formal methods and abstractions, but it was very accessible. At least I learned a great deal. I'm going to see if there is anybody who has got a quick question for you. And while people may actually think of a question, I can ask a question. There is this term that I have heard a lot being used in security to say we want to have our software or our systems secure by design, which in addition, instead of trying to kind of build walls and protect against bad guys later on and so on, by design it was secure. So can you comment on what that secure by design philosophy, paradigm, and this software designed by contract, which is what yours is, if there is a relationship between them, if you could quickly comment on that.
Yeah, absolutely. I mean, I think the idea of having something be secure by design kind of goes back to this idea of writing a full specification for code and then trying to come up with a piece of code that suits the specification and perform full verification. And I think I guess as I introduced things in the beginning of this talk, I said that I think this plays into the sort of worse is better problem, which is that it's just too high a bar. It's a firm concern. It's a discrete firm concern that we have that we sort of that is all or nothing. And if we're forcing ourselves to get above that bar right at the beginning, it's too tall an order. And so people in practice just don't do things that way. And I think what design by contract gives us a way to do is write small granular contracts right into our code that supports the idea of having sort of readable self-documenting code, and that allows us to rapidly prototype code as we're developing contracts for it, but then still gives us many of the same benefits of having a specification in that we have our code protected at least dynamically. And I think in the future, we'll be able to turn these contracts into full verification, as I've mentioned. And so I think it also gives us a bridge to still being able to accomplish what we'd really like, which is fully verified code that we know and can prove is correct.
Thanks. Anybody has got a quick question? You could unmute yourself and ask, or you could put it in the chat. And I want to remind James also to put the link for the survey for today so the students can complete it. Anybody has got a quick question? There's a question that just got put in the chat. So I don't know, Tom, if you can see it. Christopher is asking, with contract-based coding, can we possibly use it to prototype even faster? Is the question.
Yeah, I think it helps you prototype correct code faster. That's what I would say. I mean, the addition of writing a contract is going to slow you down. But so if you're okay writing incorrect code, then it's always going to be a little faster to just do away with the contract. But I think what it allows you to do is write correct code a bit faster.
So on that note, Tom, this is obvious. Like when you have these things inbuilt into your code, there will be an overhead in terms of runtime, right? Mm-hmm. But how much is it? So if you really wanted to get an idea, so maybe I could be okay if my code is twice as slow as it should have been. That could be tolerable. But how much of an overhead are we talking about in general?
Yeah, I think the overhead is pretty considerable, actually. I mean, just think about how much slower a language like Python is from a language like C++, right? And that kind of gives you a sense of the difference. You know, if you write simple, straightforward code in Python, there may be no good reason why it couldn't be as fast as C++. But what Python does is adds a lot of interpretive overhead that slows things down. And what contracts represent is just, in a sense, more of that kind of interpretive overhead. It's not really interpretive overhead, but it's safety monitoring overhead. And in higher level languages, you almost always have these kinds of guards, even if you don't have an actual contract system. When you run, when you run a function that's supposed to add two numbers, if you instead gave it a string and a number, and that's not valid, it should give you an error instead of just crashing horribly. And so all of that is accomplished by having code that's monitoring it. So even without a contract system, higher level languages are always going to have tons of monitoring, and that's really what makes them so much slower. But I think the advantage of contracts is that you can put in contracts where you need them and not add contracts where you don't need them. And that hopefully in the future we will be able to get the best of both worlds by adding contracts and then still having compilers that remove those contracts when they compile. And I think we're seeing more and more approaches that do work this way. JIT compilation has gotten so much better in the last decade or two. You know, I think JavaScript, for example, is a great example of this. There's been a lot of good work in different kinds of JIT-based compilation and optimization that are able to remove lots of the easier low-hanging fruit dynamic checks that are easy to remove, and that has massively sped up JavaScript. And so I think it gives us a gradual approach to being able to make the code faster and faster. But admittedly, if you don't perform that optimization, adding all these checks do slow the code down quite considerably. And it's similar to the difference between a statically compiled language with types like C++ or Rust versus a very high level language with a lot of interpretive overhead like Python or JavaScript.
I think we can squeeze in Ralph's question and we will stop after that. If you can read, Ralph is asking, are all contracts statically verifiable? What are the limits of what can be done statically?
Yeah, that's a great question. So basically, if you were to impose any bound on how much work you're willing to put into verifying a contract, then no, you can't guarantee that that all contracts will be verified, because basically this comes down to the halting problem. Any kind of program property that you might want to verify about code is as difficult as the halting problem. And so ultimately, you can always come up with tricky properties that are more difficult than any fixed system for verifying those properties could possibly manage. But I think in practice, we can always make systems for verifying code more and more and more expressive and powerful so that in practice, we can accomplish most of the verification that we care about.
Right. Thank you very much. For those of you who are in 317, we'll talk about halting problem towards the end of the semester. If this were a word that you wondered, what is he talking about? We'll talk about that. Thank you very much, Tom. We will stop here. Next week, we will have the next CISR seminar, just a week from today. Normally, we would have it in 2 weeks, but for this time, we are going to have 3 seminars in the